Welcome back. Welcome back to the fourth lecture of this course. So in the previous lecture we had talked about complex numbers and complex maps. We said how complex numbers were related to rotations and dilations, and how the conjugate map is a reflection along the real axis, and the 1 over z map is the reflection along the unit circle, and how to visualize these maps which are from complex plane to complex plane by looking at the real and imaginary part and seeing how they map straight lines and circles, and look at the maps which actually preserve uh, the family of lines and circles, and these are special class of conformal mappings and so on. So in this lecture we are going to define the notion of derivative for complex functions, right? Which is the so when we prove the fundamental theorem of algebra, we use the Cauchy integral formula, which was a property of holomorphic functions. So holomorphic functions are a class of functions in the complex plane, and they have a very nice property and so on. So we are going to look at holomorphic functions, and it's related to Cauchy-Riemann equations, which is a first order system of PDE. So let's get to the lectures. So let's look at start with the notion of derivatives. We all know what is the notion of derivative for a real valued function on R. So if you have a function from R to R, you say it's differentiable at a point A. We denote it as f prime of A if this limit exists, right? Whenever this limit exists, then you call that as the derivative of the function. Okay? This is something which we know from your real analysis. And we also know that not all functions are differentiable. Something like mod x is not differentiable at 0. In fact, um, you can find functions which are nowhere differentiable and so on. We will see it sometime later in this course. So this is the notion of differentiation on the real line, right? And we want to generalize this notion to the complex plane. Before we do that, let's look at the generalization of differentiation to normed linear space. Okay, so this is called the Frechet derivative. So this is the notion of differentiation in the norm linear space. So you have a open subset of a norm linear space E, and you have a map F from the open subset omega to another norm linear space F, and we call this little f to be differentiable at a point A in omega if there is a linear map dfa. So LEF means, so this is a set of all linear maps between E and F. So we say this little f is differentiable at A if there is a linear map such that this limit tends to 0. So this is motivated from the previous definition of the real variable. So recall that we said that derivative basically means is looking for a linear approximation to the function at a point, right? So what we did here is something like that. Like we looked at the chord joining the 2 point x and a, and we make the chord as small as possible. We get and if that limit exists, then that's the derivative, which is the slope of the tangent at that point. Now this we can rewrite as the following. F prime of A is independent of x, right? So I can bring it this side. So we will have minus f prime of A, and then multiply this x minus a with f prime of a, so that you have a common denominator. So you have fx. So in the numerator you will have fx minus fa minus f prime of a times x minus a over x minus a, limit of x going to a, right? So what you have here is an f prime of a acting on x minus a, and that limit goes to 0. And we have already seen in the previous lecture that this is a real number. So this real number can be, every real number can be associated to a linear map, right? So you can think of this number as a slope of the tangent. You can also think of this as a linear map, which means it's the linear approximation to the given function at a. So in that sense, so taking that variant of this definition is how you get this definition. You have fx minus fa minus a linear map acting on x minus a over x minus a. Because now we are not in real numbers, there is no notion of derivative. So what you divide is the norm, basically the distance goes to 0. Okay, so this is the notion of, this is what is called the Frechet derivative of the given function little f. If the function is differentiable in all the points of omega, then you say that this little f is differentiable in omega, like you say even in a classical case, right? And then you can think of this differential derivative of f as a map from the domain omega to the set of all linear maps, because for every point, suppose it's differentiable at all points of a, then at every point of a you have a linear map dfa. So you actually have this map. Okay. Now in the special case, when these norm linear spaces are actually Rn and R, I mean the Euclidean spaces or finite dimensional spaces, but finite dimensional spaces are all equivalent. So we can, without loss of generality, we can consider Euclidean spaces. So this is what you study in your multivariable calculus or several variable calculus. This is what is called the total derivative, which is the linear approximation for a given function. So in this finite dimensional situation, this Frechet derivative is nothing but the total derivative. The fact that assumption that we have made that omega is open is only to ensure that this existence of this linear map that you have is unique. Okay. So this is the generalization of the notion of derivative to any norm space. In particular, now we can have notion of derivative or total derivative from R2 to R2. So earlier I had defined from R to R notion of derivative. This is actually much more general. You can have between any two norm linear space. You can have between R2 to R2, R2 to R3, R3 to R3, all possible situations. Right? We have the most general definition of derivative here. The next is the generalization of what is called the directional derivative. So you must have seen in your several variable calculus that there is a notion of directional derivative in the higher dimension, right? In the case of one variable, it coincides with the usual derivative because there is only one direction, right, in the real line. Whereas in higher dimensions, the moment you go to R2, there are infinite directions. You can approach a point from around the point from anywhere. So there are infinite directions there. So we can take the notion of real derivative and apply it along a line through that point, along every possible line through that point. This is the notion of directional derivative. This can be generalized to any vector space. So this is called the Gateau derivative. So Gateau derivative is the generalization of directional derivative to any vector space. You see, for the Frechet derivative, we had asked for a norm linear space, which means it's just not a vector space, it is a vector space with a norm on it, right? Which means there's a topology on it. So it's a topological vector space, which is why you could talk about the open set there, right? So for that definition, you require that because you are using the norm in the limit definition, right here. But to give the notion of Gateau derivative for a real valued function, so it's a function which is on a vector space. and its real value. So say this vector space is over R. Okay. This vector space is over R only, then it when you say HV here, it has to make sense. So this vector space is over R, and you're looking at a real value function. So then the Gateau derivative is defined as 1 over H Fa plus Hv minus Fa. This limit has to exist, and that is called the directional derivative of f at A along the direction V, where V is any non-zero vector of the vector space. This is the notion of directional derivative, right, or the Gateau derivative. So in particular, when your vector space is a finite dimensional vector space, and if you choose your little v, so the direction to be the standard basis vector, say the jth basis vector, then this definition reduces to your jth partial derivative, right? So for each j, you have the partial derivative. You can also talk about this for any vector space V, and in Rn you actually have a norm, right? You have a notion of distance, so you don't have to do this for all direction V. You can do it for vector V with unit norm, right? Because otherwise it's fine. So for any, when we say any non-zero vector space, I mean any non-zero vector from the vector space, in the case of Rn, you can scale it to the unit circle. So you can just take directions by choosing vectors on the unit circles. And this is the property between, so this is the relation between the directional derivative along any vector V and the partial derivatives. This actually comes from the fact that any vector in Rn can be written in terms of the basis vectors Ej. So any vector V in little v in Rn can be written in terms of the basis vector, right? Summation Vj, Ej, so on. And we can use that information to actually prove one set of inequality and so on. So this is a relation between the directional derivative of f at A along a vector V is nothing but the dot product of the partial derivatives with the given vector. Then you have this notion of Jacobian matrix. How is this coming in? So as I said, the Frechet derivative or the total derivative that we defined is a linear map now, right? So on a finite dimension space, if it's from Rn to Rm, it is a linear map, and you know from linear algebra that every linear map corresponding to the basis, you have a matrix representation. So the total derivative will also have a matrix representation, right? And that matrix is what is called the Jacobian matrix. So how do you obtain this matrix is basically, if you look at any function f from Rn to Rm, then this f has exactly m components. So each fi here, each fi is a map from Rn to R, right? And because there is Rm here, you have m components for f. And the linear and the matrix representation of the linear map that of the derivative at A is given by the gradient of fi's. So gradient of fi's are given in on the rows, right? So these are the gradient of fi's. So you have a m cross n matrix, right, which is actually a map from Rn to Rm. So you should have an m cross n matrix. So you have a m cross n matrix. This is the matrix representation corresponding to the total derivative of f at A. Okay, this is something. So, and this is what is called the Jacobian matrix. And the determinant of the Jacobian matrix is denoted by this symbol Jf of A. And look at the, so whenever you do the change of variable and so on, you have this determinant of Jacobian matrix has to be taken care of, right? So this is the Jacobian of the, so the determinant of the Jacobian matrix is J of A. Okay, now let's get to the complex derivative. So in the it's very similar to the real derivative, right? So the derivative of a complex function at any point A is whenever this limit exists, and that is defined as the derivative, the same as the real derivative. The only difference in the sense that the difference from the real derivative is that in the real derivative, when you set this limit z going to a, it can either come from the left or come from the right. So there are only two possible directions in which it can approach that limit in the real case. Whereas in the complex plane, the z approaching a are infinite directions, something like in R2. But you see in R2 we did not have this notion of derivative because there is no notion of division in R2. So this is complex plane is like R2 with some arithmetic on it or some algebraic operations, multiplications and divisions given on it, right? So because we have this division notion, we can talk about this derivative. But in this case, now you have infinite directions approaching here. But the definition is same. So it looks so. On the first two, it looks like the definition, which is true, that the definition is very similar to the real variable definition, but the consequences are completely different due to the nature of the complex plane and so on. Right, that's what you must have seen in your course in complex analysis, which we are reviewing now. So this is so a function is complex differentiable whenever this happens at the point A. Now, what is holomorphic? A function is said to be holomorphic at A if it is complex differentiable in a neighborhood of A. Okay, so there is a difference between complex derivative and holomorphic function. Complex differentiation means that the function is differentiable at the point A. If the function is differentiable at the point A and in the neighborhood of A, also in the neighborhood of A, then you call that as a holomorphic function at A. Okay, so holomorphic function is something much more restrictive than complex differentiable, complex derivative. I can give an example. So look at this example of z going to mod z square. This function is complex differentiable at the point A equal to 0. You can verify this definition. But it is not holomorphic at A equal to 0 in the sense that in any neighborhood of so there is no neighborhood of 0 in which this function is differentiable. It is only differentiable at 0. Everywhere else it's not differentiable. So this is not holomorphic. Okay, z going to mod z square. The other nice property of this holomorphic function, the fact that you impose this extra condition that it has to be differentiable in a neighborhood of A, actually says that the derivative is always, so if it's holomorphic at z0, then the derivative is also continuous. So you see this is not true in real line. So see, this is not same as, so there is this result that if a function is differentiable, then it is continuous, right? I am not saying that. Here I am saying that derivative is continuous, right? That result says that if a function is differentiable, then the function itself is continuous. That's fine. That's true even here. If it's complex differentiable, then it is continuous, right? Here we are saying something more. Here we are saying that if a function is holomorphic at z0, then the derivative at z0 is continuous. This is not true in real line because you know this example that if you take x square sine 1 over x for x not equal to 0 and at x equal to 0 you take 0, this function is will admit a derivative. You can compute that. You will have it, so at 0 it will be 0 and at x not equal to 0 there will be the derivative of this by the product rule that you apply. So you will have a derivative of this, but that derivative is not continuous. This is in the real line, whereas for holomorphic functions that does not happen. So what is the proof of this fact that holomorphic function, so for a holomorphic function, its derivative is continuous. It actually follows from the Cauchy's integral formula, which we have already used and which we will see later the proof. So once you have Cauchy integral formula, this is a consequence, right? In fact, once you have that, you actually have that it's infinitely differentiable and so on, right? So from there it follows. So the way you should understand this is the Cauchy integral formula is, in a sense, is giving you a kind of primitive or anti-derivative. So right, so it's giving the function in terms of some integral. So it's giving. So if you differentiate that function, you get something else. So in a sense, you are writing it as a primitive. So naturally, it has to be continuous because if the function is differentiable, then the function is continuous, right? So the primitive is differentiable, and so on. I mean, not primitive is differentiable. The function is differentiable because you have an integral form of the function, so it is continuous. Okay. So this is the proof of that fact. That is follows from Cauchy integral formula. Okay. Now, as I said, this is not true for real derivatives. Real things are much more. So as I said, complex numbers and complex functions and differentiation is a much more restrictive thing. It only captures a very special cases, very nice situations which we see in R. Right? So in the R, what we see as analytic functions. This corresponds to that. All these holomorphic functions corresponds to that analytic functions. So, but in the real case, the derivative is not continuous. The closest that you can get to this property that holomorphic function derivative is continuous is the intermediate value theorem. Okay, and that's a property which is weaker than continuity. So the derivative, so in the real case, the derivative is not need not be continuous, but the derivative will always satisfy the intermediate value theorem. Okay, so in a sense, the complex for the holomorphic functions, it's giving you something more. The derivative is continuous. Okay, fine. Now let's look at a property of the holomorphic function. In fact, a necessary and sufficient condition is the Cauchy-Riemann equation. So let's look at this definition here again. So this definition tells you that whenever this limit exists, then that is called the derivative. So let's take a point A. So without loss of generality, let's take the point, let's say 0, A is 0, right? So we are looking for A is 0. So let's take two situations where a z approaches 0. So suppose z is all such that the imaginary part is 0, that is, it is all lying on the real axis and approaching 0, right? Then if you compute that, I mean using that, because z is all real now, right? A is 0. What you're doing here, this is just a real number here, right? So this is a real number here. So if you use that property, and similarly you now use the other path. So the first I chose the real path. Now you choose the other path to approach 0, which is the imaginary axis. So it's purely imaginary. So the real part is 0. So you approach the 0 from the imaginary axis. Then what you have here is a imaginary number here, right? Imaginary number multiplied. So some iy or something like that. So, and if the function is differentiable, then both these limit, whether I take the path on the real line or whether I take the path on the imaginary line, they should coincide, right? So if you do that exercise, that's what I'm saying here. If you choose the path z minus a going to 0 as purely real, and similarly z minus a as purely imaginary, what we will get is this equation, right? Because when you just take along the x-axis, what you get is the partial derivative of the function with respect to the x. Similarly, when you do it from the imaginary axis, what you get is the partial derivative of the function. So suppose f, so this f has this real and imaginary part, then depending on the path that you choose along real and complex, you get these two different equations, and both should be equal to x. which means both these should be equal. So here if you equate the imaginary, the real part and the imaginary part, you get what is called a first order system of equation, which is called the Cauchy-Riemann equation. Right? There are two, so all these are partial derivatives. There are two functions u and v. So you have a system of equations which is called the Cauchy-Riemann equation. I'm going to show you. So what is that you get? I mean, if you equate, you get ux is equal to vy. That is the x derivative of u is equal to the y derivative of v at a. Similarly, the x derivative of v is equal to the negative of y derivative of u at a. So that's the Cauchy-Riemann equation. Okay, and it's a first order system of equation, right? You have u, v, two functions, and they satisfy a system of PDE, partial derivative, because it involves partial derivative. Now there is this result which we will not prove here. You can look at any complex analysis book and you must have seen it in complex analysis course. One way, anyway, we have checked here. The other way can also be proved, that if so, any complex function is holomorphic if and only if its real and imaginary part satisfy the Cauchy-Riemann equation. So for any function f which is differentiable, its real and imaginary part satisfy this equation that I told you, ux equal to vy and vx equal to minus uy. Now if you start with two functions u and v which satisfy this Cauchy-Riemann equation, then the u plus iv will be a holomorphic function. This is this result. Okay. So here you see we have the assumption that it's holomorphic. So this if and only if, so this necessary and sufficient condition is for holomorphic function. If instead of holomorphic, if you just impose complex differentiability, which as I said is a much weaker condition, right? If you put complex differentiability, then you should demand here that the real and imaginary part admits a partial derivative and the partial derivatives are continuous and so on. We don't need that assumption for holomorphic, but for complex differentiability you need that continuity of partial derivatives assumption. Anyway, so for holomorphic function you have that the real and imaginary part satisfy the Cauchy-Riemann equations. These are the Cauchy-Riemann equations that I mentioned. So ux is vy, which is the second equation here, and vx is minus uy, which is the first equation here. So this is a system. So this is the first order system of PDE. In fact, you can show that this is actually an elliptic system of PDE. So there is a notion of classification for system of PDEs, the way you have for second order PDE classifications as elliptic, parabolic, hyperbolic, and so on. You have a similar classification depending on the eigenvalues and so on found by the coefficient. You can have a classification. So this is the elliptic first order system of PDE. Now this we can rewrite. Just for convenience, let me rewrite in a better way. So this can be seen like this. So this system of PDE is precisely the yth partial derivative of the vector uv is this matrix acting on the x partial derivative of the vector uv. If you have come across in your PDE what is called the linear transport equation, right? This is the first order PDE. This looks like that, but now it's a system of equations. So this more or less looks like a system of first order PDE, which very similar to the transport equation. Okay, and this coefficient is given here, right? And in fact, you can also see this in another way. For instance, instead of writing here uy and vy, you could have written here as vx. So vx vy, which is the gradient of v, equal to the same matrix ux uy, which is the gradient of uv. So gradient of gradient of V is equal to the matrix acting on the gradient of U. Okay. And what is this matrix? This matrix, you can see, is actually the rotation matrix. This is the matrix which rotates a vector by 90 degrees, right, pi by 2. So this is the rotation matrix. In fact, in the previous lecture we associated every complex number with the rotation matrices. So this is actually the matrix that corresponds to the complex number I, right? If you take the complex number I, so its real part is 0, so 0 0 on the diagonal here. Its imaginary part is 1, so it's 1 1 1 minus 1 here. So this matrix is precisely the complex number I, right? And in fact that property is also preserved. For suppose you square this matrix, you will see that you will get negative of the identity matrix, and I square is minus 1 as complex number, right? And minus 1 corresponds to the negative identity matrix. So the complex number minus 1 corresponds to the rotation matrix negative identity matrix, right? So this is that. So there is, you see this deep underlying connection lying here. So this is kind of related to I. So the other property that I said, instead of uy here, for instance, what I am saying here is, instead of writing uy equal to minus vx, write this as vx equal to minus uy, right? Just bring the uy here and vx there here. Then the same relation holds where you will replace this uy by vx. So you have vx vy here, which is precisely the gradient of v from the same matrix, and here you will have ux uy, which is the gradient of u. So what is this saying? That the Cauchy-Riemann equation is actually saying that if you take the gradient of u and rotate it by 90 degree, what you get is the gradient of v. That is the gradient of the real part rotated by 90 degree gives you the gradient of the imaginary part. You see that, right? So this is what I'm saying in the next slide, that that equation, so the Cauchy-Riemann equation also tells you that the gradient of the imaginary part can be obtained by a pi by 2 rotation of the gradient of the real part. In fact, the Cauchy-Riemann equation also tells you that the gradient of u is orthogonal to gradient of v, right? That is what this means, right? When you rotate gradient of u by 90 degree, and if you get gradient of v, that means they are orthogonal, and that's what this means. In fact, that you can even see directly here. If you want this to be orthogonal, what you want is ux vx plus uy vy should be equal to 0. You use the Cauchy-Riemann equation, you will get mixed derivatives, it will be equal to 0, right? So this Cauchy-Riemann equation actually connects the real part and imaginary part. In the sense, you cannot fix arbitrarily both real and imaginary part. Once you fix the real part or imaginary part, the other automatically gets fixed. Once you fix a function u as the real part for a holomorphic function, if you fix the real part, then the imaginary part gets fixed automatically. It is just the 90-degree rotation of the gradient of the real part. That is the gradient of the imaginary part, right? So geometrically, this also means, in a sense, so in the sense of change of variable, the way you can see is this: that if you look at these level curves u, right? If you look at these level curves u, then what happens is grad u is the normal to this level curve, right? So if you, when I say level curve, so you fix a c, then you look at all the x and y such that u is mapped, so the real part is mapping it to the number c, right? So if you look at this set of all xy such that it's equal to c, uxy is equal to c, that set, for that that will be a curve in the complex plane, right? Because u is a map from c to r. So the graph of u is in R3. So when what you're saying is you fix it C on the range, and you look at all xy in the domain for which this happened. So that's going to trace some curve in the complex plane. So that's why it's called level curve, right? So to this level curve, so the normal to this level curve is gradient of u. So gradient of u is normal to this level curve. And we already know that gradient of v is orthogonal to gradient of u, which means gradient of v should be tangential to this level curve. Sorry, this should be u equal to c here. Okay, this is u equal to c. That's a typo here. U equal to c. So grad v is tangential to u equal to c. Similarly, if you do this for v, you get that grad u is tangential to this level curve. So what this and grad u and grad v are orthogonal, which means these two level curves are orthogonal system of curves. So this is actually the change of variable, which is what we did in the previous lecture. If you remember, when we plotted the z square and the e power z, we took the real part and imaginary part and so on. So this is like, see, in R2, suppose you take x equal to constant, right? When you take x equal to constant, what you get are all the vertical lines. When you take y equal to constant, what you get is all the horizontal lines, right? They are orthogonal family of lines, family of curves, right? And they form the basis in R2, right? These vertical and horizontal lines form the basis in R2 if you choose any two lines. Similarly, here, if you choose ux to be some constant, vx to be some constant, the Cauchy-Riemann equation for a holomorphic function, if these are real and imaginary part of holomorphic function, or if these u and v satisfy the Cauchy-Riemann equations, then they actually form an orthogonal system of curves. So these are all geometry that lies underneath the Cauchy-Riemann equation. Okay. And this is something I already commented about, that the rotation matrix that you had is actually corresponds to the complex number I, and you can verify that the square of that matrix is actually negative identity matrix, which is another one, which is also a rotation matrix. Right? So as I said, so for a holomorphic function, you cannot independently choose real and imaginary parts. If you choose one, the other gets fixed automatically, and that's what Cauchy-Riemann equation tells you. Plus, Cauchy-Riemann equation also tells you some properties between the real and imaginary part, like the gradients or orthogonal and so on. Now let's compare between the complex derivative and total derivative. Compare in the sense that you remember that we said the complex derivative, the complex map is from C to C, and C can be seen as R2. So any complex map can be seen as a map from R2 to R2, and in R2 to R2 there is a notion of Frechet derivative or total derivative, and from C to C there is a notion of complex derivative. And we have seen that the definitions are different, right? In R2, I mean, the definition we use for total derivative in R2 is not same as the definition in C to C, but in both the places we were looking for linear approximations. And we have already seen in the previous lecture that complex linearity is a much more restrictive condition than real linearity, right? So when you are saying complex differentiable, you are putting much more restriction than when you say total derivative, right? So that is what we are going to compare here. For instance, suppose you take a function f and you take a point z. I'm missing. What am I missing here? Yeah, that's fine. I mean f is with real part uv, which is a function of x and y. When I say x and y, I mean the real and imaginary part of the complex number. So if I take any z here, the way I associate it with R2 is via this real and imaginary parts x, y. So any map from C to C can be seen as the same map can be seen as f of xy going to u of xy comma v of xy. Right? Okay. So these are the components of f and these are the components of the argument. So the total derivative of this map, of this complex map, but seen as from R2 to R2, is f prime of the derivative is f prime of f, will admit a matrix representation. We saw that, right? So you have a 2 cross 2 matrix representation. So the total derivative will have the matrix representation, which is nothing but, as I said, the row or the gradient of the components of f. The component of f is u and v. So gradient of u and gradient of v. This is the Jacobian matrix corresponding to the total derivative of this function, which is from C to C. Okay. Now, if you use Cauchy-Riemann equation, actually I should say holomorphic function here, okay, but it's fine. Anyway, complex differential also satisfies holomorphic, so it's, also satisfies Cauchy-Riemann equation. So, by the Cauchy-Riemann equation, you replace this uy by minus vx, and you replace this vy by ux. So what you get now is a matrix of the form where this diagonal is same and this diagonal has the same with opposite signs. This is precisely like a rotation matrix, corresponds to a complex number, right? And that's what you get here. So all the complex derivatives are actually those real derivatives which are of this form, which are of the rotation form, right? That is what the Cauchy-Riemann equation actually gave you. The other way of writing this is, instead of using the Cauchy-Riemann equation on the second column, you use it on the first column. That's what this is. So you have both these options, and both represent a complex number. So what is the complex number this represents? Where the real part is x derivative of u and the imaginary part is vx, right? So the RHS is a rotation dilation matrix form that corresponds to a complex number, and this part here is precisely the partial derivative of f with respect to the x variable, this matrix, and the second matrix here is precisely the partial derivative of f with respect to the y variable, but the minus sign is here, not here. So you actually have a minus I. So minus I of the partial derivative of y is precisely this matrix. Okay. And so the determinant of the Jacobian matrix is just the modulus of these partial derivatives. So you see, because complex linearity is a much more restrictive condition, complex derivative is also a restrictive condition compared to the total derivative, right? So it's a very smaller class than the total derivative. This is why we have these nice properties that we have in complex differentiation. This is another connection between Cauchy-Riemann equation and fluid flow in 2D, in two-dimensional fluid flow. So there is a notion of this ideal fluid flow, which is ideal fluid flow means that the fluid flow is both incompressible and is irrotational, right? Incompressible basically means that you cannot compress it, right? It is not something like a gas can be compressed and so on, right? So, and irrotational means there is not, so the fluid is, so during the flow, the fluid does not show too much of vortices or rotations, right? Because that are complicated things to understand. So an ideal fluid flow is one that is both incompressible and irrotational. Mathematically, what incompressibility means is that the divergence vanishes. So divergence of the velocity of the fluid vanish. That's what incompressibility means. And irrotational means that the curl vanishes. So vanishing divergence implies incompressibility, and irrotational means that the curl of the velocity vector vanishes. So now if you think of u comma v as a velocity vector field of a fluid flow in 2D, okay, then the fluid is ideal if and only if it's incompressible and irrotational, means the divergence of the velocity vector is 0 and the curl of the velocity vector is 0. So divergence is precisely this, which is ux plus vy equal to 0, and the curl is vx minus uy equal to 0. Now what does this look like? Which means ux equal to minus vy and vx equal to uy. So this looks like Cauchy-Riemann equation except for the sign. So in other words, if you think of a fluid flow in 2D, the ideal fluid flow corresponds to the fact that the velocity vector u comma minus v satisfies the Cauchy-Riemann equation. Okay, which means if u comma minus v satisfies Cauchy-Riemann equation, which means that the function u minus iv is holomorphic. So ideal planar fluid flow can be completely understood by looking at holomorphic functions, where the real and imaginary part of the holomorphic function will denote the uh, velocity components of the fluid. Okay, so this nice connection we have, this way we can completely understand two-dimensional fluid flow. So you see the nice applications that you have just from the definition of complex derivative and so on. Now finally, let's look at some examples here, and here I am looking at functions, complex functions which are real valued. That is, it's a map from C to R. It's not from C to C, but C to R. For instance, uh, for any map f from C to C, its real part is a map from C to R. Its imaginary part is a map from C to R. So these functions have some nice property. So let's see it from some examples. So look at this function z going to mod z square. This function we have already seen that this is not complex differentiable except at 0, right? I showed you that this was complex differentiable, but it's not holomorphic, right? I gave that example. So this is a complex differentiable function, except it is not a complex differentiable function except at 0, whereas the corresponding map in R2, which is precisely this map, that is x comma y going to x square plus y square. This is precisely the analog map in R2 of this mod z square. This is differentiable everywhere. And you can prove this because you can see that this will admit partial derivatives, and partial derivatives are continuous and so on. So you can actually write down the Jacobian matrix and you have this derivative. So this map as a function of R2 is differentiable, but as a complex function it's not differentiable, right? So that comparison that we made between complex derivative and total derivative. There is a total derivative for this map. I mean, it is total differentiable, but it is not complex differentiable. And notice the fact here that this is a map which is from C to R. Let's take this example, which is any complex number mapped to its real part. Now this function again is not complex differentiable, and you can see that this function is actually an extension of this identity map in R, x going to x, right? That's a linear function that's actually differentiable in R, right? And this z going to real part of z actually extends this. So sometime back in some in the, I think, the fundamental theorem of algebra lecture or somewhere, I had talked about extending uh, real polynomials to complex functions and what kind of extension should look for, like analytic continuation, all that I talked about. I mean, I just mentioned about that. So here you see this function x going to x is extended by this function, but this x going to x is real differentiable, whereas this function is not complex differentiable. So you actually have a non-differentiable extension to a real differentiable functions. Whereas if you choose this z going to z, the identity map on C, that is a nice extension to this identity map on R, right? So this is a good extension for this map, seems right. So this is what I talked about, analytic continuations and so on. So and again you see this is a map, z going to real part of z is a map from C to R, and that also turned out to be not differentiable. In fact, this property is true for any function from C to R. So there's nothing special about mod z square or real part of z, right? If you take any function which is from C, which is real valued on the complex plane, so either if it's a constant function, fine. Either it's a constant function. If it's not a constant function, then it cannot be holomorphic, right? And how do you verify this? Cauchy-Riemann equation. Because if the function f is from C to R, that means the imaginary part of that function is 0, right? Where you can say, imaginary part of the function is 0, right? So, which means that v is 0, only u is remaining, and for the function to be holomorphic, it has to satisfy the Cauchy-Riemann equation. If u is not a constant function, then it cannot satisfy the Cauchy-Riemann equation, so the function cannot be holomorphic. Okay, so this is a nice property about holomorphic functions and its connection with Cauchy-Riemann equation. I think we'll stop here. Hope you get something, you have understood, and you develop some intuition with these lectures. See you next lecture. Thanks a lot. Bye.